Okay, we're going to look at here next in section 7.2 is we're going to be working on finding areas between curves. Now, the good news is that we already have a pretty good idea of how to do that. We've had several examples of problems where we had some F curve up here and some G curve down here, and if we want to find the area between those two, we know that if we found the area underneath F and the area underneath G, and we subtracted them, we would get the area between them. And that rule still holds here in this particular part. And if you look at on your page 375, they have the definition there of area between curves here. And one of the things that this depends on, though, is that the F curve is always above the G curve. So if we write an integral of f of a to b, if you will, and we have f of x minus g of x, then the one thing that this relies on is the fact that f is always above g. Okay? If we had a situation like this, for instance, where I had my f curve here and my g curve here, and I wanted to find the area, okay, from 0 to, let's say, 8, let's say for argument's sake. If I want to find that area, okay, would I get the right answer if I just did straight f minus g from 0 to 8? Okay. The answer is no, because ultimately what would happen if I, in this area right here, my f values minus my g values would give me something negative. Would that give me the total area here? No. Okay. So there's two options here what I had to do. Actually, there's only one option in this case. Really, the only option is to find that point. Let's just say it was at 5. And if we separated those two, okay, from 0 to 5, the top function is f, the bottom function is g. So we could write an integral from 0 to 5 of f minus g. Okay, and then we could go add that to 5 to 8 of the top function this time is g minus the f function, which is the bottom function in this case. And if we add those two together, then we would get the total area enclosed by those two curves on that interval. Okay? So the key issue here, though, when we write the integral is that when we write it, okay, if we do an f minus g situation, okay, that means the f function has to be the top of the interval the whole entire way. Okay, if it's not, then we have to make some kind of adjustment. Okay. All right. So the problem next I want you to look at here is on page 317, or 377, I should say. This is a problem that can be handled in a couple different ways. This is example 4. We have a situation where we have the square root function, okay, and then we have the function x minus 2. Okay. And so ultimately our picture looks something like this. Okay. And we need to find the area of this region. Now, we have a little bit of a problem here in that we want the area of the region that's enclosed by the x-axis, the line, and the curve. Okay. Ultimately, if I were to continue to draw this here, and I missed my 2 a little bit here, so make an adjustment. So 1, 2. Okay. If I wanted just the area between the two curves, then I could just do a straight f minus g because that radical x function is always on top, the line's always on the bottom. So I could just do straight f minus g. Now the problem though is that I don't want this part. Okay. I just want this part only that's in the first quadrant. Okay, so my boundaries aren't just the two curves, they're the two curves plus the x-axis, if you will. And so we want just this part only. And so my question is then, how do we find just that part only? Well, we got a couple options. Okay, in fact, we have 3 options, really. Okay, we could go ahead and just do the f minus g. We could go from 0 to where they intersect, which is 4 of the square root minus the line dx. Okay, that right there would give us the answer. Okay, but again, remember what I just said, though, that would give us the answer for everything, including that x part. True? So think about what would I have to do to get rid of the x part? Well, what shape is the x part if it's made by a line and two axes? Triangle. It's just a triangle. So couldn't I just subtract the area of the triangle, which ultimately in my case would be a 2 by 2 triangle, so it would be minus 2 times 2 times a half would be 2. Okay. So if I did that minus 2, that would give me an answer to this question.
You have to add it.
What's that?
You have to add it.
No, you take that away.
Remember, if I do this function, okay, which is on the top, and I do this function, which is on the bottom, that would give me this whole entire area right here. But I don't want this part right here.
That is taking away from the top function of it to like take away and taking away. You have to add what's on the bottom.
Oh, ultimately, this integral right here is giving me this whole thing right here.
Yeah.
Okay. All right. So if it's giving me this whole thing, though, I don't want that x part in there. So I want that x part to be out. Okay. So this integral, if I do top function minus bottom function, is going to give me the whole entire, including the x part. Okay. But we want the x part out, so that's why we're doing the subtraction part. Okay.
Oh, is he saying because there is negative yet you have to add it?
Say it again.
Because it's below the x-axis, you take it away. Like, the area of x is negative, right? Because it's below the x-axis.
Right, but ultimately, again, we're finding the total area of this shape right here is going to be, the negative area is going to get accounted for just by the functions themselves here. So, you know, like I said, if we found the total area here of this shape that I have here, the entire shape, that's going to be this, okay? Because it's an f minus g situation because f is always on top, g is always on the bottom, okay? And ultimately, we need to subtract that triangle out of the total area that we find, okay? So again, the total area, just like we did up here, whether it's above or below, is going to always be found if the f function's always on top, g function's on the bottom. Okay, the total area is going to be found with f minus g. Fair enough? Okay. And we can test these here in a minute with some other information here in a minute. But the other option that we have here too would be if we split this into two, since the bottom changes, okay, of this region that we're interested, the shaded region. If we did an integral from 0 to 2 of just radical x dx, that would give us this part right here, wouldn't it? Give us the area between the curve and the x-axis. Okay, just this part right here. And then if I added to that from 2 to 4 of the radical minus the line, okay, that would be another f minus g situation. True? Because again, I'm going from 2 to 4 here. This is 2, this is 4. So if I subtracted the radical minus the g, that would give me just this part only. And if I add those two parts together, we get same answer as what we got first time, hopefully. Okay. All right. So now the other option too would be this. What if I did this? If I went from 0 to 4 of just radical x, what would that give me? 0 to 4 of radical x would give me all this, wouldn't it? Okay. And then what could I subtract off to get rid of the white part here that I don't want? I could subtract off that triangle, which is a 2 by 4 this time. This is up to 4 here. Nope, this is 2, sorry. Only goes up to 2, so it's still a 2 by 2, so we'd subtract 2 again. Alright. So let's see what happens when we try these. If we do our, let's do the split one here in the middle first. If we just found the area of this part right here, which I'll call that region 1, and we'll call that region 2, just so we can have a basis here. Alright, so that region 1, again, is just the area under the radical x curve from 0 to 2, so let's get an answer for that. So if I do my integral command here, we get that, which I don't think goes to a fraction nicely. Nope. So that answer 1.886. And then we're going to add to that, and again, remember to get this area number 2 here, with our middle, we're doing the top minus bottom situation. So let's make another integral here with our top minus bottom. So it's radical, radical x minus 2. And going on that one from 2 to 4. And we get that, 1.448. Right? And ultimately, if we add those two together, I'm just going to get an approximation here. I'm not, this obviously could be more exact here, but ultimately if we add those, we're going to get 3.334 approximately. All right, so let's try that one. Let's do the bottom one next. If we do the integral on the bottom, we got just radical x dx from 0 to 4. We get 5.333, and keep in mind there's rounding errors here because I didn't keep it exact just for time's sake. But ultimately, if we do that and then we go minus 2, what do we get? Essentially the same thing. Like I said, we got a rounding error here because we rounded that one up. Actually rounded both of those up, so that gave us an extra number here on the end, but ultimately, same deal. Now, again, in the scheme of things, if we're doing this with a calculator, we're going to put this all in at the same time, so whichever way we do it, we're going to get the same answer rounded. Let's try this one right here. If we do our integral, which I already had that in there somewhere, there it is. We'll go from 0 to 4. So that same integral here is our radical x minus 2 over here. So if we do that one from 0 to 4, we get that. And if we go minus 2, like we had up here originally, what do we get? 3.333. So, like I said, which one of those ways is the best? They're all the best because they all give us the right answer. True? So again, there's a variety of ways to find that area. The reason that really the only reason why the top and bottom worked in this particular case is because one of the functions was linear. So we were able to actually use a triangle here. So if I had two functions that were non-linear, is there going to be a triangle option? No. So ultimately, this situation would have been really the only option where we break it up into two different parts. Right? Because again, keep in mind that in order to just do a straight f minus g, okay, what has to be the case is that they not only have to be one above the other for the entire interval, okay, but they also have to be both greater than 0. If they're not, if we cross the x-axis, then that changes the rules in terms of this. All right, and so ultimately, I guess what the easiest way to think about it would be to write this in just one integral, which we really can't in this case. Okay, to write it in one integral, we'd have to have the whole top, okay, the top of the area, no matter where we drew a rectangle, because remember we started by making rectangles to estimate these areas, right? So if we do a rectangle, if I drew that rectangle right there and I drew that rectangle right there, would they both have the same top? Would the top function be the same for both of those rectangles? Yeah, that's good. Okay, but would the bottom be the same? No, so that's not good. That's why we'd have to split this up into two different parts. Okay, now ultimately, like I said, for this particular function, we'd either have to do A, split it up into two parts, do two separate integrals here, or we could use an area if it's a linear function, or here's the fourth alternative. And this is probably the best because we can write one integral only on this one. So for this particular case, if I have my drawing again, and I got something like this, let's say it look like that, and again this is y equals radical x, and this is y equals x minus 2, it's the same deal. If I recognize that I'm going to have to make two different integrals, if I see this and I want this shaded region here, and I see, all right, well I'm going to have to make two different integrals then for this one, and again that's not unreasonable, it's pretty easy to do. Okay? But one thing that's also nice is that if we notice that the reason we have to make two intervals is because if we drew a rectangle here and a rectangle here, they'd have the same tops, but they wouldn't have the same bottoms. So that means we'd have to split up the region, okay? Or use geometry for the triangles. Okay? Now, here's the alternative, though. The alternative would be if we recognize that, well, what if we, instead of having rectangles that were vertical, what if we did rectangles that were horizontal instead? If I drew that horizontal one and that horizontal one, okay, wouldn't the right-hand side of the interval always be the line, no matter where I draw the rectangle? And wouldn't the left-hand side of the rectangle be on the other curve, no matter where I draw it? Okay. I wouldn't have to split it up into two different parts because the function on the right is always on the right, and the function on the left is always on the left, no matter where I draw the rectangle. Okay. Now the question is, what good does that do me? Well, what it boils down to is if I can do that, then I can write one integral here. But what I'm going to do is I'm going to write it in y, okay, instead of an x. So in other words, I need to get y alone in these two equations first, or x alone, I should say. So, and again, this also relies on the fact that I can actually solve these two for x. Okay, if I can't solve these two for x, then I'll have no choice but to split it up and use what they were given. Okay. So, like I said, with that, if I write these in y, then my integral is going to look like this. It's going to be, instead of f of x minus g of x, it's going to be f of y minus g of y. Okay, we've written the functions here, x in terms of y instead of y in terms of x. Now, remember above, when we did f minus g, just to very simply put, f is the top, and g is the bottom. True?
Mm-hmm.
Alright, so when we did that above, so the question is what order do these need to be in to get this right? Okay, and the order is this. It's always going to be the right minus the left. So whatever function is on the right-hand side of our slice that we draw here is going to be the function we use that's going to be first, and then we're going to subtract whatever function is on the left-hand side of the rectangular slice that we draw. So ultimately, what function is making the right? It's the line. The line is on the right. True? Okay. Just look at your rectangle. Here it is. What's on the right? Is the line on the right, or is the parabola part on the right? The square root function.
Right.
The line's on the right. So that means we're going to have y plus 2 minus y squared dy. That's going to be our integrand. And that will give us exactly the same answer if we get the part 2 right here, which is what about the upper and lower limits here? Do we still go 0 to 4 like we did in the previous time? And the answer to that is no, because 0 and 4 are x values. Okay, we're integrating in y here, so we need to use y values. So instead of summing up our vertical rectangles going to the right, we're going to sum up our horizontal rectangles going from x-axis to the top, if you will. And so therefore we're going to go 0 to 2 because this intersection point, remember, was the point 4, 2. So if we were doing vertical rectangles, we'd be going from 0 to 4. If we're doing horizontal rectangles, we're going from 0 up to 2. And that'll sum up all of the rectangles, these horizontal rectangles that we've drawn. And just to double check to make sure that we have it right, we'll use our integral command again. And this time we have y plus 2 or x plus 2. Keep in mind your calculator won't put y's in there, so you need to in your mind know that these are y's that you're typing in even though they're really x's, right? Okay. And so we'll go x plus 2 minus x squared, comma x comma 0 comma 2. And sure enough, there we go. We got our 3.3 repeating again. Okay. And again, all those answers we had on the other page were just approximations for the 3.3 repeating. If we did this with the fundamental theorem, we'd find that the answer is 3 1/3. Alright, so bottom line is what makes that way better? Really the only thing that makes it better is that we can just write one integral instead of separating into two different parts and writing two different integrals. Okay, we can write it in one integral as long as we have a region that has a same right and same left throughout the whole. Okay, if it has the same top, same bottom, we can just keep it in x. If it's got the same right and same left, then we can make horizontal slices and we can do it from right to left instead of from top to bottom. Okay. Let's take a look at, go ahead and page 379 now. We have in our example 6 here at the top, we have two curves that are drawn here. One is y equals x cubed, one is x equals y squared minus 2. Which ultimately is a sideways parabola, so it's a non-function. And I guess the fact that they gave us the equation x equals y squared minus 2 might be a giveaway that it's one that we're going to want to do with y instead of x. Because if you look at the picture that we have there, again we have this parabola situation, and then we have this situation. Okay, you'll notice that if I were to try to do a vertical slice here and use x as my variable, ultimately if I drew a rectangle right there, and I do a rectangle right there, keeping in mind that this is my shaded region, what would be said about these two rectangles? The top right here would be this function, top right here would be the same function, but the bottom would be this function here, and the bottom here would be a different function altogether, wouldn't it? So ultimately we'd have to split that into two different parts. But if you notice that in the interval, what if I drew horizontal slices? What would I notice about the left and right? The right would always be the cubic, the left would always be the sideways parabola, wouldn't it? True. So with that said, I can write an equation in y, and my cubic, remember this is y equals x cubed, but we can't write it in terms of x because we're writing in terms of y. We're going to do a horizontal, so that means I'd have y cube root equals x. So cube root of y would be that part, minus, and we already have the other one solved for x, it's y squared minus 2. And so therefore our integral would look just like that. Okay. Now the other issue is what about the limits? Okay, we have the right function minus the left function in our integrand, which is what we want. Okay? The right side is the cubic, the left side is the parabola. So we have that set up correctly. Now what about the limits? We'd need to know the y-coordinates of that point and that point. True? And so ultimately, we would need to either use substitution and elimination, whatever the case may be, to figure out, well, what are those points? Well, again, we know that y cubed equals, or x cubed equals y, and we know that x is equal to y squared minus 2. So if we were to take this x and plug it in, we get y squared minus 2 cubed equals y. So that's one option, okay, would be to solve this, all right? And if we want to solve this, okay, we could FOIL it, of course, and one of the issues that we're going to have here is that we're going to wind up with a 6th degree equation, okay? And it's going to have a constant, so there's not going to be a factoring out a y at all. So we're ultimately going to have to find the solutions to a 6th degree equation. So I'm going to tell you right now, this would be on the calculator part. They're not going to expect that you do the algebra to solve that. So what's our alternative to solve that equation? Use your intersection command. So if we go ahead and put that in, we have y squared. Keep in mind, there's no y's in here. And that's all cubed, and then we have y here. And see if we see an intersection. And we do, in fact, see 2 intersections, which is good, because we are looking for 2 points here. One that's, we know that one of the y's here is negative, one is positive. That looks good, too, because we can see that the 2 intersections have a positive and a negative. So if we do our second calculate and an intersection command, go up by that first intersection point, and we get -1. Well, that's convenient. So it turned out to be an easier answer than we thought there, and we might take a guess at what the other one is here. It's probably going to be what? Probably 1 based on the symmetry, but just double check here. Oh. Move that over to the other intersection point. Hit enter 3 times. We don't get 1, which is not what we expected, so that's a good thing we did it, right? Mm-hmm. Right? And so that right there would be our value for the upper limit. And keep in mind that I would make sure that if I'm going to type that into my calculator now to find an integral answer for it, that I use all the decimal places. So again, we'll go do our math 9, and we have y cubed here, so x to the 1/3, all right. Instead of having to try to find that cube root button, it'll be minus x squared plus 2. It'll be our integrand, and we go -1. 1.793037. Calculate. Get our answer, which is 4.215. That'll do it. Alright, so again, key piece of information is that when we have the situation where we have where the top and the bottom aren't always the same, where the bottom changes somewhere in the interval, or the top changes in some interval, okay, we have a choice to either split it up into different parts, which may or may not prove to be difficult, okay, or we can just do it from right to left if we have the same right and same left. It's just as easy to do it same right and same left. Okay. Alright, so ultimately, our assignment here for tomorrow, or for Monday, is to work on our syllabus problems. I think it's 3 through 33 is the start. We're going by 3s, I believe. So you got some that are going to be in y like this, some that will be in x, like the previous ones that we looked at. Okay. So let's give some of those a try, setting up the integrals. I'm going to tell you that